Our next speaker is Dr. Chenming Hu. Chenming has been called the father of 3D transistor for leading the FinFET development in 1999, which is a fundamental technology leading to the production of 3D transistor, Intel's most radical shift of production in semiconductor technology in over 50 years. Chenming is a board director of SanDisk Corporation. He is also a board director of nonprofit Friends of Children with Special Needs. From 2001 to 2004, he is the Chief Technology Officer of TSMC, the world's largest dedicated integrated circuit manufacturing company in the world. He was the founding chairman of Celestri Design Technology until the acquisition by Cadence Design in 2002. Chenming has authored 4 books and 900 research papers and has been granted over 100 US patents. He is honored by membership of 3 national academies: the US National Academy of Engineering, the Chinese Academy of Science, Academia Sinica. Chenming has received UC Berkeley highest honor for teaching, the Berkeley Distinguished Teaching Award. He received bachelor degree from National Taiwan University and MS and PhD from UC Berkeley in electrical engineering. He is currently researching green tunnel transistor for ultra-low power electronics. Chenming's speech today is New Transistors in Our Future. Let's welcome Dr. Chenming Hu.
Ladies and gentlemen, it's an honor to be invited to share some thought with you today. This is one way of looking at the semiconductor technology from the top. You can see that this being a semiconductor professionals gathering, I don't think I'll get objection when I say semiconductor these days are really running the world. So that's the top, says the world. And what's helping the world run is some thousands of IC companies making tens of thousands of chips, different kinds of chips now. And these companies uses about perhaps a dozen of companies to fabricate their chips. Many are foundries, others are integrated companies. And all these foundries, all these chips basically use the same transistor. And not only that, if you look at this transistor, if you take a cross-section of it, it really hasn't changed much from the day the transistor was first invented. So, May 4th, there was a front page article by New York Times. It was written in cooperation with Intel to announce Intel's announcement of moving to a 3D transistor. And the New York Times article says that Intel would use 3D FinFET. FinFET is not a preferred name by Intel for this transistor, but the research community is known as FinFET. It's a name that I had the honor to give it in 1999. And Intel will start using this at 22 nanometer later this year. And as you know, once a move of that is made, it's not going to be reversed. Other companies actually have announced even before then to use FinFET, but at 14 nanometer. So the question is whether they're going to pull in somewhat because of Intel's announcement. The article quoted Gordon Moore saying that this is the most radical shift in semiconductor technology in 50 years. And the last part of the New York Times article also says, now some people think there's another new transistor that will be a considerable competition to what the choice that Intel has made. And I want to tell you a little bit about that competitor as well. So these are the two transistors. In fact, there's a third one I'll mention at the end. But these are the two that the New York Times article mentioned. On top is transistor called a FinFET. We call this FinFET because the shape of the transistor, you can see, has to do with a thin piece of silicon sticking out from the flat chip. And it has the shape of the back fin of a fish. So we call this a FinFET. And the other transistor that article talked about is known as ultra-thin body SOI. I also had the pleasure of naming this transistor because it was developed in the same time as FinFET. And the second transistor called ultra-thin body SOI because, first of all, SOI stands for the idea that the silicon transistor is built on an oxide. Ultra-thin body refers to the fact the transistor body really has to be very thin. Now, we're not talking about, just the fully depletion, partial depletion, if you happen to know that term. We're talking about making this body only 4 or 5 nanometers thick, about 15 silicon atoms thick. It's very, very thin, and that's what's needed. Now, before I tell you about these new transistors, let me just remind you a little bit what the transistor we have been using for 50 years look like, or 40 years look like. It's, of course, what we have been teaching our students all these years. It looks like the cartoon on the left. There's a source, there's a drain. Current flows between the source and drain. And very importantly, there's a third terminal called a gate. It's the gate, that gate voltage determines whether currents flow through this device or not. If otherwise, you would have a resistor. Because the third terminal, which determines whether current flows or not, we have a transistor. And I'd like to lead you a little deeper into this picture. The way the gate does this is that between the source and drain, there's a barrier. We call that potential barrier. It's like the gate of a reservoir, a dam. You lower this gate, then the water from one side, from the reservoir will flow out of the dam. If you raise this gate, that flow stops. And that's, in fact, why this is called a gate. It gates that flow. So what the gate voltage does is that lowers and raises this potential barrier, therefore allowing the current to flow, electrons to flow, or not allowing it to flow. Now, looking at a little more detail, we usually describe how effectively the gate does this by plotting the current versus the gate voltage. We like the transistor to look like this bottom curve, this red curve. It's a better design. That is, when the gate voltage is reduced, the current drops very rapidly. By the time gate is current voltage 0, we have very small leakage current left. We call that off-state current, I off. And that's what we really want. That is, the transistor changes from on to off with a very small change in voltage at the gate. But if you don't design the transistor well, we know that it can look like this other curves, the black curve, the blue curve, and in fact, the very badly designed transistor will look like the top curve. That is, it's really not a transistor anymore. Now, what the problem we're facing is that no matter how carefully we design the transistors, the best designed transistor is looking more and more like a very badly designed transistor when the transistor gets smaller. Smaller these days simply meaning putting the source drain closer together, make that gate smaller. When you make gate smaller, indeed the transistor have become in the last decade more like this black curve than blue curve. You probably have never seen this a transistor that looks like the top curve, because when engineers saw that transistor, we just throw this into the wastebasket. We never write a paper about it. But that's exactly where the transistor headed if we keep making the transistor smaller and smaller. The best designed transistors are looking like what we used to call very badly designed transistor. And because of that reason, I-off is now getting to be bad. Not only that, the transistors or I-off is becoming very sensitive to size and dopant, meaning sensitive to the manufacturing variation. We call that CD, critical dimension variation. So not only the transistor is bad, we don't even know how bad it is because every transistor looks a little different than its neighbors, than the transistor on another chip. That makes design very difficult. Another reason that the device variation large is called the dopant variation. You know, we put dopant into the semiconductor in different ways, but no matter how we do this, the actual number of the dopant in a small transistor is not the same from one to the other. The reason is that in a very small transistor, there are only 20, 30, maybe even 10 dopant that determines its characteristic. Now, when you put 10 things on average into a billion bucket, the average you can control very well to be 10 each bucket. But because it's randomly distributed, you simply throw this atom by ion implantation into 10 billion buckets. Within each bucket, it could be 10, most likely, but some will have 9, some will have 11. They're not too bad, but those with 5 and 15 will have very different characteristics than what you really want. So that's the problem that's causing a lot of device variation. And the result is that we're using higher voltage and paying the price of higher power and using high design costs to deal with this. So Intel is the first company to decide the pain is big enough, let's do something to go away from this problem that the conventional transistor cannot help us solve anymore. So let's take a look at why I-off and the variation are getting very bad. There's a very easy way, simple way to look at that. That is, the gate controls that potential height, the dam gate of that reservoir, through this capacitance. When the gate voltage raises and lowers, the potential barrier raises, lowers, control the current. The problem is that this picture is good when the channel length is long, when the gate is large, but when the channel becomes very short, the drain becomes very close to every point in the channel. Imagine if the gate drain becomes very close to the source, and no point in the channel is far away from the drain. You know, both the drain and the gate get voltages, positive voltages. And both the drain and gate have capacitance that controls the potential of the channel. So the drain is playing the role of a second gate. But that's not what we want. If the drain plays the role of the gate, and drain alone determines whether current flows or not, that's a resistor. That exactly is the problem we're facing with. Small transistors will look like resistors because the drain has too much control compared to the gate. It doesn't have to have as large control. Even if you have 10% to control the gate, it's already giving us a problem that we cannot handle today. And that basically is the problem. Now, for those of you who are semiconductor experts may be thinking, well, you know, we have always been able to deal with this problem simply by making the oxide thinner and thinner. Well, that's running into a problem not only because the thin oxide had leakage problems, reliability, but I'm going to show you a more fundamental reason that we realized in the 90s, a little earlier than other people, that told us that even the best high-K ideal dielectric in the world would not allow us to shrink the transistors. So I'd like you to think about this thought experiment. Suppose you had just invented a perfect insulator to replace this SiO2 oxide so that you can make the gate dielectric very, very thin, and yet there's no leakage problem, no reliability problem. So you can make the gate oxide very thin. And this makes the gate capacitance to the channel infinite. And therefore, the gate has perfect control of the potential height, that gate height, that the dam gate height at the surface. Would that allow you to make the source and